Right now, the universe is breaking the rules. Two telescopes are looking at the same cosmos, asking the same question, and getting two different answers. One says space is stretching at one speed. The other swears it's moving faster. Both can't be right. Both refuse to be wrong. We'll show you a void 2 billion light years across that may be hiding our galaxy, dark energy that seems to be dying, and a crack in physics so deep it could rewrite everything we know about reality. If this sounds like your kind of mystery, smash that like button and subscribe. Settle in. We begin. Picture two scientists standing on opposite ends of a long hallway. Both are holding rulers. Both are measuring the same wall. One says the wall is 100 feet long. The other says it's 110. Neither will back down. Neither is making a mistake. This is exactly what's happening in cosmology right now, except the wall is the entire universe. For nearly a century, we've known space is stretching. Galaxies are flying away from each other. The farther they are, the faster they go. Scientists call the speed of this stretching the Hubble constant. It's one of the most important numbers in all of physics. Get it right, and you know the age of the universe, the size of the universe, even how it might end. There's just one problem. Nobody can agree on what the number is. The first method looks at the leftover glow from the Big Bang. Imagine the universe as a giant pot of soup that boiled over almost 14 billion years ago. The faint warmth from that explosion is still everywhere around us. Scientists measure that warmth and run it through equations. The answer comes out to about 42 miles per second per megaparsec. Don't worry about the unit. Just know it means the early universe is whispering one specific number. The second method ignores the early universe completely. Instead, it watches stars in our cosmic neighborhood, pulsing stars called Cepheids, exploding stars called supernovas. Each one acts like a cosmic mile marker. Scientists measure how fast nearby galaxies are running away, and the answer comes out to 45 miles per second per megaparsec. 3 miles per second doesn't sound like much, but across billions of light years of space, that gap explodes into a chasm. It would mean the universe is hundreds of millions of years younger than we thought, or older, or built from materials we haven't discovered yet. For years, scientists assumed someone was just making a sloppy measurement, a telescope mirror slightly off, a star mislabeled, a calculation rounded the wrong way. So teams across the world checked, they double-checked, they triple-checked, they built better telescopes, sharper instruments, more precise math. The gap didn't shrink, it got worse. In April of 2026, a massive international team called the H0 Distance Network released the most precise measurement of cosmic expansion ever made. Hundreds of astronomers, decades of data, multiple telescopes. They squeezed the uncertainty down to barely 1%, and the answer they got? 73.5 kilometers per second per megaparsec. The high number, the same stubborn answer the local universe has been screaming for years. The conclusion shook the field. This work effectively rules out explanations of the Hubble tension that rely on a single overlooked error in local distance measurements, the team wrote. Translation: it's not us. The mystery is real. Something inside the universe is hiding a secret. Something is making space expand differently than every equation predicts. And the deeper scientists dig, the weirder the answers get. Because the next clue isn't hiding in the math. It's hiding in our own backyard, a bubble, an empty pocket of space. And we may be sitting right in the middle of it. Imagine you're standing in the middle of a desert. You look around and see nothing but flat sand for miles. You measure the temperature. It feels normal to you. Then someone tells you that just beyond your horizon, the entire planet is covered in jungle. Your reading wasn't wrong. Your location was unusual. The desert lied to you about the rest of the world. This might be what's happening to humanity right now. On a cosmic scale, in 2013, 3 astronomers named Ryan Keenan, Amy Barger, and Lennox Cowie were counting galaxies. They used infrared telescopes that could see through cosmic dust. mapping millions of stars in every direction around the Milky Way. They expected to find galaxies spread evenly, like grains of sugar dusted on a table. Instead, they found something disturbing. Our cosmic neighborhood is unusually empty. The team measured a region almost 2 billion light-years wide. Inside this region, galaxies are about 10 to 50% less dense than the rest of the universe. A massive underdense bubble in the cosmic ocean. They named it the KBC void after their initials. Some scientists prefer the term local hole. Either way, the implication is staggering. Earth is not floating in an average patch of space. Earth might be sitting near the center of the largest known emptiness in the observable universe. To picture the scale, imagine the entire visible cosmos as the surface of the Pacific Ocean. The KBC void would be a circle wide enough to swallow most of North America, and we, with all our stars, all our telescopes, all our science, are floating somewhere in the middle of that hole. Why does this matter? Because of how gravity behaves inside a void. When a region of space contains less matter than its surroundings, the surrounding matter tugs everything inside the void outward. Galaxies get pulled toward the dense edges, like passengers being yanked toward the walls of a spinning carnival ride. From inside the void, every galaxy looks like it's running away faster than it really should be. These peculiar velocities would largely point away from us, creating an extra redshift that boosts the local measurement. Translation: if we live inside a giant cosmic bubble, every measurement we take of nearby expansion is biased. We'd see space stretching faster than it actually is, simply because we're standing in an unusual spot. This could explain the entire mystery. The early universe measurement, taken from the smooth glow of the Big Bang, sees the cosmic average. The nearby universe measurement, taken from inside our void, sees an inflated number. The two answers disagree because they're measuring two different things from two different places. It's elegant, it's clean, it's the kind of solution physicists love. There's just one terrifying problem. The standard model of the universe says voids this big shouldn't exist. Not at this scale, not in our cosmic neighborhood. The math says a hole this large forming in the time the universe has existed is roughly a 1 in a billion event. So either we are the cosmic lottery winners, sitting in a freak structure that our equations swore was impossible, or our equations were wrong all along. And the next discovery makes that second possibility much harder to ignore. Imagine you've watched the same river flow past your window for 30 years. Every day, same speed, same direction, same calm rhythm. Then one morning, you notice the water is moving slower, just slightly, then slower still. You measure carefully. You're sure. Something is changing. Something that, by every law of nature you've been taught, was supposed to be unchanging. This is exactly what scientists discovered about dark energy in 2025. Dark energy is the strange force pushing the universe apart. It makes up roughly 70% of everything that exists. We can't see it. We can't touch it. We can't even properly explain what it is. We just know that ever since galaxies first formed, dark energy has been stretching space faster and faster, like an invisible hand pulling on the fabric of reality. For decades, physicists treated dark energy as a constant, the cosmological constant, a fixed, unchanging value baked into the universe like the speed of light. Einstein himself first introduced the idea more than 100 years ago. It was simple, it was elegant, it worked. Then came the dark energy spectroscopic instrument. Astronomers call it DESI. It sits on top of a mountain in Arizona and stares at the sky with 5,000 robotic eyes. Each one collects light from a different galaxy at the same time. Over 3 years, DESI mapped the positions of nearly 15 million galaxies, building the largest three-dimensional map of the cosmos in human history. When the data came back in March of 2025, it broke the constant. DESI tracks dark energy's influence by studying how matter is spread across the universe. The new analysis, using the largest 3D map of our universe ever made, looked at dark energy's influence over the past 11 billion years. The map showed something nobody expected. Dark energy isn't constant, it's weakening. In the early universe, the push was strong, stretching space fast, accelerating galaxies apart with brutal force. But somewhere along the way, the push started to soften, not by much, just enough to register in the data. As one cosmologist described it, dark energy used to be pushy, now it's getting tired. If this is real, the implications are colossal. The cosmological constant, the rock that physics has been built on for decades, is wrong. The universe isn't running on a fixed setting, it's running on a dial, and someone, or something, is slowly turning it down. The lead researcher on the analysis, Mustafa Ishaq Bushaki, said something that should send a chill through every astronomy classroom on Earth. If this continues, then eventually, dark energy will not be the dominant force in the universe. Therefore, the universe expansion will stop accelerating and will go at a constant rate, or even in some models, could also stop and collapse back. Read that again. The universe could stop expanding. The universe could collapse. Scientists are still cautious. The signal hasn't reached the gold standard certainty physics demands, but every new dataset has only strengthened the result. And while the world argues about what it means, an even stranger discovery is waiting in the same data. Because the way dark energy is changing isn't just unexpected, it's pointing somewhere terrifying. Every villain in physics has a name. Some have two. Dark energy might just be the only mystery in the universe that has both a phantom and a quintessence working against each other inside the same equation. To understand what that means, picture a giant cosmic spring. When you stretch a spring, it pulls back. That's normal matter. That's gravity. Now imagine a spring that pushes outward instead of pulling inward. The more space stretches, the harder it pushes. That's dark energy. Now imagine a spring that pushes harder when stretched, then suddenly stops pushing, then slowly starts pulling backward. That's what the latest DESI data seems to suggest. Scientists have given names to the different ways dark energy might behave. Quintessence is the name for a gentle, well-behaved version. It pushes outward, but the strength of the push slowly fades over time. The universe keeps expanding, just less violently. Galaxies drift apart forever, but more peacefully. Then there's the phantom. The phantom is the nightmare version of dark energy. It pushes outward with growing strength, faster and faster, until eventually space itself rips apart. Stars, planets, atoms, everything torn into nothing. Cosmologists call this scenario the Big Rip. Until recently, most scientists thought the phantom was a wild, theoretical fantasy, just math with no real connection to reality. Now the data is whispering that both might be real. At different times, a study published in late 2025 looked at every major dataset together: the cosmic microwave background, the DESI galaxy map, the Pantheon Plus collection of exploding stars. When researchers fit all the data into one model, they found something deeply strange. Early universe constraints favor a phantom phase, while late universe data prefer quintessence. The full dataset suggests a late-time interaction between dark energy and matter. In plain language, dark energy seems to have switched modes. Long ago, it was the phantom, getting more aggressive over time. Then something flipped. Now it's the quintessence, getting weaker. And it might be touching ordinary matter in ways physics never accounted for. Nothing in our standard model allows for this. The cosmological constant is supposed to be one number, frozen forever, not a shapeshifter, not an entity that goes through phases like the moon. The fact that the data suggests this kind of behavior is forcing scientists to invent entirely new categories of physics. Some theorists have proposed even darker possibilities. One group, looking at the same data, found a 93% preference for the universe transitioning into something called anti-de Sitter space. That's a fancy term for a universe that eventually collapses back on itself. A cosmic implosion, the opposite of everything we've been told for the last 50 years. Imagine being told your house is shrinking. not falling apart, shrinking. The walls slowly closing in, the ceiling lowering, the floor pulling up. That's what the universe might be preparing to do, if these models are right. Most scientists still treat the cosmological constant as the safest bet. It's simple, it's beautiful, it's been right for a long time, but beauty isn't truth, and the universe doesn't owe us elegance. What's even harder to swallow is that the strangeness doesn't stop with dark energy. The very fabric of space, on the largest scales we can see, isn't behaving the way the equations demand, and that brings us to another problem entirely. There's a rule in cosmology called the cosmological principle. It sounds boring. The name is dry, the textbooks are dry, the equations are dry. But this rule is the foundation under every model of the universe ever built. Take it away, and physics has no floor to stand on. The rule says this: on large enough scales, the universe should look the same in every direction. Stars and galaxies should be sprinkled like pepper across a tablecloth. Zoom out far enough, and any patch of space should match any other patch. Average density, average distribution, average everything. For most of the 20th century, this rule held up beautifully. Telescope after telescope confirmed it. The early universe, captured in the cosmic microwave background, looks almost perfectly smooth in every direction we point. Tiny ripples here and there, but otherwise uniform. Then the maps started getting better, and the universe started looking lumpy. The KBC void was just the beginning. Astronomers have since identified massive cosmic structures that shouldn't be possible inside the standard model. There's a stretch of galaxies called the Sloan Great Wall, more than 1 billion light-years long. There's another, larger group called the Hercules Corona Borealis Great Wall, stretching nearly 10 billion light-years. That's almost a quarter of the observable universe wrapped into a single connected structure. According to the cosmological principle, structures this large shouldn't exist yet. The universe is only about 14 billion years old. There hasn't been enough time for gravity to pull matter together over distances that vast. Building a wall that big is like assembling a skyscraper out of dust grains in 5 seconds. The math says no, the sky says yes. Then there's the dipole problem. Quasars, the bright cores of distant galaxies, should be spread evenly across the sky. They're not. There's a slight excess in one direction and a deficit in another. The pattern matches what you'd expect if the universe had a preferred axis, a lopsided cosmos, a universe with a head and a tail. Each individual anomaly could be a coincidence, a statistical wrinkle, a measurement error, but they keep stacking up. The voids, the walls, the dipoles, the mismatched expansion rates, the weakening dark energy, all pointing to the same conclusion. The cosmos isn't smooth. The cosmos isn't uniform. The cosmos has structure on scales the standard model says are impossible. Some researchers have started exploring what physics looks like if you simply throw the cosmological principle away. The results are dramatic. If space isn't smooth, then galaxies can't be used as honest distance markers. The light from a star traveling through dense regions slows differently than light traveling through empty regions. Time itself ticks slightly differently inside voids. Apparent expansion rates become illusions, distorted by the lumpy terrain the light traveled across. This idea is called inhomogeneous cosmology. Most scientists still resist it. The standard model has been too successful for too long. But every year, more data forces the question: what if the universe was never smooth to begin with? What if every measurement we've ever taken is being filtered through a cosmic landscape we still don't fully understand? The deeper this question goes, the stranger the implications become. Because if smoothness is broken, it's not just expansion that's wrong, it's our entire picture of how matter and energy are spread across space. And that picture has another, even bigger crack in it. The crack is called dark matter, and the latest measurements suggest it might be missing. Roughly 25% of everything in the universe is supposed to be dark matter, an invisible substance that doesn't shine, doesn't reflect, doesn't interact with light at all. We've never seen a single particle of it directly. We've never trapped one in a lab. We've spent billions of dollars building detectors deep underground, in old gold mines and abandoned tunnels, hoping a single dark matter particle would brush against a sensor and tell us it exists. After 40 years of searching, the detectors are still silent, but we're sure dark matter must be out there, because the math demands it. Galaxies spin too fast for their visible mass to hold them together. Without an extra layer of invisible glue, every spiral galaxy should fly apart, like a merry-go-round losing its bolts. Galaxy clusters orbit each other with too much speed for their visible weight. Light from distant objects bends around clusters as if guided by something massive we can't see. So scientists invented dark matter to make the equations work. Extra mass to anchor the galaxies, extra gravity to bend the light, 5 times more matter than the visible kind, spread invisibly across every galaxy, every cluster, every empty pocket of cosmic space. For decades, the picture held together, until cosmologists started counting it. Modern surveys, including DESI and other gravitational lensing experiments, have been trying to weigh the universe, not by looking for dark matter directly, but by measuring its effect. How strongly does it pull? How clumpily is it distributed? How much of it is needed to explain the structures we see today? The answers keep coming back lower than expected, anomalously lower. A measurement called the S8 parameter tracks how clumpy dark matter is in the present-day universe. Predictions from the early universe say it should have a certain value. Observations of galaxies today say it has a smaller one. Just like the Hubble tension, the gap won't close. The early universe is whispering one number. The late universe is whispering a different one. If dark matter is real, but it's clumping less than predicted, that means something is smoothing it out. Some process we don't understand. Some force pushing matter apart faster than gravity can pull it together. Possibly, the same dark energy that's mysteriously weakening. Or it could mean dark matter isn't what we thought. Maybe it's not particles at all. Maybe it's a flaw in our theory of gravity, showing up at vast scales where we can't test it in a lab. A theory called Modified Newtonian Dynamics, or MOND, has spent 40 years arguing exactly this. MOND tweaks the rules of gravity for very weak fields and explains a lot of galactic motion without needing any invisible particles at all. For most of its history, MOND has been treated as a fringe idea. The standard model with dark matter was simply too successful to abandon. But as the cracks in that model multiply, as every survey finds new tensions, as every detector keeps coming up empty, the fringe ideas are starting to look less fringe. The next decade will decide. New experiments, better telescopes. The James Webb Space Telescope is already finding galaxies that formed earlier and grew faster than the standard model predicts. The Vera Rubin Observatory will soon scan the entire southern sky every few nights. The pressure on the old model is building. And if dark matter falls, dark energy falls with it. And if both fall, the entire structure of modern cosmology has to be rebuilt from scratch, brick by brick, equation by equation. But before we tear it all down, there's one more shocking observation to consider. Because the James Webb Space Telescope just saw something that shouldn't exist. The James Webb Space Telescope is the most powerful eye humanity has ever lifted into space. It floats nearly 1 million miles from Earth, shielded from the sun by a sunscreen the size of a tennis court. Its mirrors are coated in gold. It sees in infrared, the kind of light that travels best across cosmic distances. When Webb looks at the early universe, it's looking at light that left its source over 13 billion years ago. What Webb has seen is breaking the textbook. According to the standard model, the early universe was supposed to be quiet. After the Big Bang, hot plasma cooled, atoms formed, the first stars ignited slowly. Galaxies built themselves up gradually, merging from smaller clumps over hundreds of millions of years. By the time the universe was 300 million years old, only baby galaxies should have existed. Small, dim, unfinished. Webb looked at that exact era and found the impossible. Massive galaxies, bright, fully assembled, stuffed with stars. Some appear to contain almost as many stars as the Milky Way does today, except they formed in a fraction of the time the Milky Way had to grow. Astronomers have a nickname for these objects: universe breakers. The label isn't an exaggeration. The galaxies are so unexpectedly massive and so unexpectedly early that they violate the basic predictions of how matter should clump in a young cosmos. Picture this: you plant a seed. 48 hours later, you walk back to check on it. Instead of a sprout, you find a full-grown oak tree, 3 stories tall, leaves rustling in the wind. That's the level of impossibility we're talking about. Galaxies that took billions of years to form in our model showed up in a few 100 million years in reality. Some scientists have proposed escape hatches. Maybe the early stars were unusually bright, fooling Webb into seeing more mass than is actually there. Maybe the cosmic ruler has an error in it, making distances seem shorter than they are. Maybe early galaxies just compressed star formation into incredibly intense bursts. Each explanation has been tested. None of them fully resolve the problem. Others have started asking whether the universe itself is older than we thought. If cosmic expansion played out differently than the standard model predicts, then the time available for galaxy formation might be longer. A few extra billion years would solve the puzzle. But adding billions of years to the universe contradicts almost every other observation. So that solution creates more problems than it fixes. Then there's the most uncomfortable possibility. Maybe galaxy formation isn't what we think it is. Maybe dark matter behaves differently than our equations describe. Maybe stars in the early universe formed through a process we haven't discovered yet. Each of these explanations chips away at a different piece of standard cosmology: the expansion rate, the age of the universe, the role of dark matter, the behavior of dark energy, the smoothness of space, the growth of structure. Every single pillar is now being shaken at the same time by different observations in different parts of the sky. And the strangest part is how all these mysteries seem connected. Solve one, and the others might fall into place. Or solve one, and the others might collapse the entire field into a deeper crisis. There's a clue hidden in this mess. A pattern. Something that connects the early galaxies, the weakening dark energy, and the bubble around our galaxy. Some scientists think it points to a force we've been missing all along. A force that might be hiding inside the fabric of time itself. What if time isn't what we think it is? What if every clock in the universe ticks differently, depending on where it sits, what surrounds it, and how empty the space around it happens to be? What if the reason cosmic expansion looks weird isn't because space is misbehaving, but because time is? This idea is called timescape cosmology. It was developed by a New Zealand physicist named David Wiltshire, and for years it sat on the edge of mainstream science. Not anymore. Recent analyses have shown that timescape may match observational data just as well as standard dark energy models. Maybe better. The idea works like this. Einstein taught us 100 years ago that gravity bends time. The stronger the gravity, the slower time flows. A clock at the bottom of a deep gravity well, like next to a black hole, ticks slower than a clock floating in empty space. This isn't theory. It's been measured directly. GPS satellites have to correct for this effect every second, or your phone would lose miles of accuracy in a single day. Now, zoom out. The universe isn't a smooth, even soup of matter. It's full of huge filaments where galaxies cluster densely, and enormous voids where there's almost nothing at all. Inside dense regions, gravity is stronger and time runs slightly slower. Inside voids, gravity is weaker and time runs slightly faster. This means the universe doesn't have one age. It has many. A clock sitting in the middle of a void has been ticking for slightly longer than a clock buried inside a galaxy cluster. The difference per second is tiny, almost invisible. Multiply it by 14 billion years, though, and the gap becomes significant. Wiltshire's argument is that when we measure cosmic expansion, we're averaging across regions where time has flowed at different rates. We don't account for it properly. because our equations assume smooth space-time, so the apparent acceleration of the universe might not be real. It might be an illusion created by light traveling through a patchwork of fast time and slow time regions, fooling our measurements into thinking the universe is speeding up when it isn't. In late 2024, a team of researchers ran timescape cosmology against 1,500 Type 1a supernovas. The results were striking. The model fit the data without needing dark energy at all. Not as well in some areas, better in others. Either way, the analysis showed that you can't simply dismiss the idea anymore. Imagine being told that the entire 70% of the universe you call dark energy might just be an accounting error, a consequence of physics not being careful about how time works in lumpy space. The most expensive mystery in cosmology dissolved into a measurement bias. If this is right, the consequences are extraordinary. There would be no big rip, no mysterious phantom force, no invisible pressure stretching space, just a universe behaving exactly as Einstein predicted, with our equations finally catching up to the messy reality of a cosmos that isn't smooth. The catch is that timescape cosmology is hard to test definitively. Voids and clusters are everywhere, and untangling their effects requires data of stunning precision. The Vera Rubin Observatory and the Euclid Space Telescope are now collecting that data. Within a few years, the model will either be confirmed or quietly buried. But if it's confirmed, it would be one of the biggest revolutions in physics since relativity itself. A reminder that the strangest mysteries sometimes have the simplest answers, hiding in plain sight all along. The next mystery, though, isn't about time. It's about light, specifically, light that took 14 billion years to reach us, and somehow seems to be carrying a message we never expected to find. About 380,000 years after the Big Bang, the universe finally cooled enough for atoms to form. Before that moment, space was a thick, glowing plasma. Light couldn't move freely. It was constantly absorbed and re-emitted, like trying to walk through a crowded subway car. Then, in a single cosmic instant, electrons paired up with protons. The fog cleared. Light suddenly had nowhere to scatter, and it began streaming across the universe. That ancient light is still around. It's been traveling for nearly 14 billion years, gradually stretching as space expanded. Today, it arrives at our telescopes as faint microwave radiation, just a few degrees above absolute zero. Scientists call it the cosmic microwave background. It's the oldest light in existence. It's also the most important map ever made. When astronomers look at this light, they see a nearly perfect snapshot of the infant universe. Tiny temperature variations, less than 1 part in 100,000, reveal the seeds from which every galaxy eventually grew. The pattern of these variations encodes everything about the early universe: how fast it was expanding, how much matter it contained, how much dark matter, how much dark energy. The map gives us the recipe for the cosmos itself. For decades, the recipe matched our model beautifully. Then better satellites looked closer. The Planck satellite mapped the cosmic microwave background with unprecedented detail. Its results gave us the lower expansion number, the 42 miles per second per megaparsec. From that data, scientists predicted what the universe should look like today. They predicted how fast galaxies should be moving, how clumpy matter should be, how warm certain regions should be. Almost every prediction has come up slightly off. The Hubble tension is the loudest disagreement, but it's not alone. The S8 tension shows that matter today is less clumpy than the cosmic microwave background predicted. There's also something called the lensing anomaly. The way light bends around galaxy clusters doesn't quite match the predictions either. And in the cosmic microwave background itself, there are strange patches, cold spots that are colder than they should be, patterns that seem to align in directions that shouldn't have any preferred axis. One of the most famous is the CMB cold spot, a region of the sky almost 1 billion light-years across where the temperature is mysteriously lower than the average. The standard model says cold spots this large shouldn't exist. Some researchers have proposed that it's actually a supervoid, an enormous empty region that drained energy from the light passing through it. Others have suggested wilder ideas, including the imprint of a collision with another universe, brushing against ours during the chaos of cosmic inflation. The cold spot remains unexplained, just like the dipole, just like the strange angular alignments, just like the tensions between early and late measurements. What this all suggests is that the cosmic microwave background and the present-day universe are telling slightly different stories. The early universe says the cosmos should look one way. The late universe shows it actually looks another way. Either the cosmic microwave background is hiding secrets we haven't decoded yet, or the rules of physics changed between then and now. That second possibility used to be unthinkable. The laws of nature were supposed to be eternal. Constants were constants. Equations didn't evolve. But as more anomalies pile up, scientists are starting to take seriously the idea that the rulebook itself might shift across cosmic time. If even fundamental constants can drift, then everything we think we know is up for grabs, including a number that has shaped science since Newton himself, a number called gravity. Gravity is the most familiar force in the universe. You felt it every second of your life. Drop a coin and it falls. Throw a ball and it arcs. Step off a roof and you'll learn the lesson the hard way. For 300 years, Newton's equation for gravity ruled physics. Then Einstein refined it. Space-time warps around mass. Objects follow the curves. The math was beautiful. The predictions were perfect. Or at least, they seemed to be. Then galaxies started misbehaving. In the 1970s, an astronomer named Vera Rubin measured how fast stars orbit at the edges of spiral galaxies. According to Newton and Einstein, stars far from the galactic center should move slowly, like the outer planets of our solar system. The farther out you go, the weaker gravity should get, the slower things should orbit. That isn't what Rubin found. The outer stars were moving just as fast as the inner ones, as if the galaxy were rotating like a solid disk, not a gravitational system. By all the rules of known physics, those galaxies should have flown apart millions of years ago. They didn't. Something was holding them together, something invisible, something massive. That was the moment dark matter became necessary. Scientists added invisible mass to galaxies until the math worked again. 5 times more invisible matter than visible matter. A cosmic ghost holding everything together. But what if dark matter doesn't exist? In the early 1980s, a physicist named Mordechai Milgrom proposed something heretical. He said maybe there's no dark matter at all. Maybe the rules of gravity simply break down at very low accelerations, the kind found at the edges of galaxies. Tweak the equation slightly for those regions, and galactic rotation curves fall into line. No invisible particles needed. The idea is called modified Newtonian dynamics, MOND. For decades, it was treated as a curiosity. The standard dark matter model was simply too successful at predicting other things. But MOND has slowly been refining itself. Modern versions, including a theory called MOG, can now explain galaxy rotation, galaxy cluster behavior, and even some features of the cosmic microwave background, all without invoking dark matter. What's even more startling is that MOND seems to predict the existence of structures like the KBC void. The standard model says voids that big shouldn't form in the time available. MOND says they should. The voids are no longer impossible. They're expected. If gravity itself is the wrong piece of the puzzle, the implications cascade. Dark matter would vanish. The need for new particles in underground detectors would disappear. The strange clumping of matter would have a natural explanation. Even some of the Hubble tension might dissolve, because galactic distance measurements are calibrated using assumptions about gravity that might need revision. The problem with MOND is that no one has ever produced a complete relativistic version that handles all of cosmology, including the cosmic microwave background. With the precision of the standard model, it works in some places. It struggles in others. The verdict is still out. But the very fact that physicists are seriously discussing modifying gravity, the most tested theory in all of science, shows how deep the cosmic crisis runs. Every safe assumption is on the table. Every untouchable principle is being examined, and the universe keeps refusing to give us a clean answer. Some researchers have started asking even wilder questions. What if gravity doesn't just need a tweak? What if it isn't a fundamental force at all? What if it's an emergent illusion, like the surface tension of water, only appearing when you don't look closely enough? That radical idea has its own following now, and to understand it, we need to dive into something called entropic gravity, where gravity isn't pulling, it's leaking. Here's a question that sounds simple but turns out to be profound. What if gravity isn't really a force at all? What if everything we feel as weight, every apple that falls, every planet that orbits, isn't being pulled by some fundamental interaction at all? What if gravity is just bookkeeping, a side effect of the universe trying to keep track of information? This idea is called entropic gravity. It was developed in 2010 by a Dutch physicist named Erik Verlinde, and it remains one of the most controversial theories in modern physics. If it's right, it would mean the most familiar force in our daily lives is actually an illusion built from something far stranger. To understand the idea, picture air pressure. When you blow up a balloon, the rubber stretches because air molecules are bouncing against the inside surface. There's no single force of inflation. It's just the statistical behavior of countless tiny particles moving randomly. The push you feel on the balloon is what scientists call an emergent phenomenon. It doesn't exist at the level of individual molecules. It only appears when you look at the bulk behavior. Verlinde proposed that gravity works the same way. At the deepest level, the universe is made of bits of information. Each bit has an associated entropy, a measure of how disorganized it is. When you bring two masses close together, you change the way that information is distributed across nearby space. The universe naturally tries to maximize entropy, the same way air molecules naturally spread out. The pull we call gravity is just the universe rearranging information to balance its books. If this sounds wild, hold on, it gets weirder. Verlinde extended his theory to explain dark matter and dark energy too. He argued that, on cosmic scales, the universe carries an extra component of entropy that behaves exactly like the missing mass we've been calling dark matter. No new particle, no undiscovered substance, just information leaking out of the way matter interacts with the vacuum of space. The math makes specific predictions, and here's the part that should make every physicist sit up. Some of those predictions match observed galaxy rotation curves remarkably well, without invoking dark matter at all, like MOND, but built from a totally different starting point. Even more striking, entropic gravity offers a possible explanation for the weakening of dark energy seen in the DESI data. If dark energy is also an entropic effect, its strength would naturally evolve as the universe expands and information becomes more dilute across larger volumes. The cosmological constant wouldn't need to be constant. It could shift, slowly, exactly the way the data suggests. Most physicists are skeptical. The idea is mathematically dense. It hasn't yet produced a complete framework that replaces general relativity in all situations. But the fact that it can make predictions in galaxy dynamics and dark energy is more than philosophy. It means the theory has teeth. It can be tested. What makes entropic gravity philosophically explosive is the picture it paints of reality. In this view, the universe isn't a set of objects sitting in space. It's a vast information system. Mass, energy, distance, even time itself emerge from how that information is arranged. We aren't standing on a planet, we're nodes in a cosmic network, feeling forces that are really just shifts in the universe's underlying data. If Verlinde is even partially right, then the deepest questions in cosmology are also questions about computation, about what counts as a bit, about where information can be stored, lost, or reshuffled at the boundaries of space. And the boundary of space might hold the biggest clue of all, because the next mystery isn't about how the universe expands. It's about whether the universe has an edge and what might be sitting just beyond it. When you stare at the night sky, you might think you're seeing the whole universe. You're not. You're only seeing the observable universe, a bubble of space about 93 billion light-years across, defined by how far light has traveled since the Big Bang. Beyond that bubble, more space exists. We just can't see it. The light from those regions hasn't had time to reach us yet. Most cosmologists assume that what's beyond our bubble looks pretty much like what's inside it. More galaxies, more clusters, more voids. The universe might be infinite, or it might curve back on itself like the surface of a giant sphere. Either way, the assumption is that the rules don't change at the edge of our view. What if they do? Some recent theories have started exploring the possibility that the universe is patchy on truly enormous scales. Not just lumpy with voids and walls, but divided into distinct regions where the laws of physics behave slightly differently. In one region, dark energy could be stronger. In another, weaker. In another, gravity itself could have a slightly different value. This idea has a name. It's called the multiverse, or sometimes the bubble universe model. It comes out of a theory called eternal inflation, which suggests that during the first sliver of cosmic time, the universe didn't expand uniformly. Instead, it inflated in a chaotic, frothy way, spawning countless separate bubbles. Our observable universe sits inside one bubble. Each bubble could have its own version of the laws of nature. If that's true, then the strange behavior we observe near the edge of our view, including the weakening dark energy and the unexpected expansion rate, might be hints of the next bubble bleeding into ours, like ripples from a neighbor's pond reaching the edge of yours. There's another possibility too. The cosmic microwave background contains a few very large-scale anomalies, patches of unusually cold sky, strange alignments of temperature variations across vast angular distances. Some researchers have proposed that these could be scars from ancient collisions, bumps where another bubble universe brushed against ours billions of years ago, leaving fingerprints in the oldest light. Most physicists are cautious about these claims. Bubble collisions are theoretically possible, but distinguishing them from random noise is incredibly hard. Statistical flukes can look like cosmic signatures. Until we have far more precise data, the multiverse remains a hypothesis, not a proven fact. Still, the idea is no longer fringe. Some of the most respected theoretical physicists in the world take it seriously, including teams working at the edge of string theory and inflationary cosmology. The reason is simple: the fine-tuning problem. The fine-tuning problem is the realization that the laws of physics in our universe seem suspiciously well-suited for life. The strength of gravity, the mass of fundamental particles, the amount of dark energy. Change any of these by even a tiny amount, and stars wouldn't form, atoms wouldn't bond, life would be impossible. Why are the numbers so perfect for us? The multiverse offers an answer. If countless bubbles exist with different settings, then of course we live in one where the settings allow life. We couldn't exist anywhere else. But the multiverse can't be tested directly. We can never visit another bubble. We can only look for indirect signatures, like the cold spots, the alignments, or unexplained shifts in cosmic expansion. Each one is a possible breadcrumb. What if the strange expansion we're seeing is actually one of those breadcrumbs? What if the universe is telling us, in its own subtle way, that it isn't alone? That would be unsettling enough. But the next layer of mystery isn't about other universes. It's about the very moment ours began, and whether that beginning was really the beginning at all. Most people have heard the phrase Big Bang. Fewer people have stopped to think about what it actually means. The standard story says the universe began about 13.8 billion years ago, when everything that exists, all the matter, all the energy, all of space and time itself, was crammed into a single point of infinite density called a singularity. Then it expanded, and here we are. The story has a problem though. Singularities aren't real. They're the point in the equations where physics breaks down, where every variable becomes infinite, where math stops giving meaningful answers. A singularity isn't a thing, it's a sign that our theory has hit its limit, which means the very beginning of the standard cosmic story is also the place where standard physics admits it doesn't know what's going on. So, what if the Big Bang wasn't a beginning at all? What if it was a transition? A boundary between something that came before and something that came after? This is the idea behind the bouncing universe model. Several versions of it exist, but the basic concept is the same. Instead of starting from nothing, the universe might have come from a previous universe that collapsed. As that older cosmos shrank, it reached a critical density. Quantum effects kicked in. Instead of crushing into a singularity, space rebounded, like a ball hitting the ground and bouncing back upward. What we call the Big Bang is just the rebound phase of an endless cycle. Recent work in a field called loop quantum cosmology has put this idea on more solid mathematical ground. By treating space as quantized, made of discrete chunks at the smallest scales, researchers have shown that gravity can naturally repel itself when matter is squeezed too tightly. At Planck scale densities, gravity reverses sign. Crushing becomes pushing. Singularities are avoided. Bounces become inevitable. If this is right, our universe isn't the first. It's the latest in a long line, maybe an infinite line. Each bounce wipes most of the information from the previous cycle, but maybe not all of it. Some researchers have proposed that subtle features in the cosmic microwave background, including those strange anomalies we already discussed, might be relics from the universe before ours, echoes that survived the bounce. This connects to our central mystery in an unexpected way. If the universe really is part of a cycle, then the laws of physics in our cycle might be slightly different from the laws in the previous one. The cosmological constant, the value of dark energy, the strength of gravity, all could shift slightly between cycles, which means there's no eternal rulebook. The numbers we observe today are just the current draft, and they might be slowly evolving. Some cyclic models even predict that dark energy weakens over time within a single cycle. The universe accelerates for a while, slows, eventually contracts, then bounces back. The DESI data, suggesting a weakening dark energy, is, in this view, exactly what you'd expect to see if you were standing somewhere in the late stages of a cycle. It's a beautiful picture. It's also unprovable. We can't see before the Big Bang. We can't directly test what happened in any prior cycle. The most we can do is look for fossil signatures, ancient ripples, subtle patterns that could only exist if a bounce really happened. So far, no smoking gun has been found, but the idea is gaining ground precisely because it solves problems the standard model can't. The singularity, the fine-tuning, the strange behavior of dark energy. A bouncing universe addresses them all at once. And if our universe is part of a bigger cycle, then maybe expansion isn't a one-way trip after all. Maybe it's just the inhale before the exhale. And the next mystery raises that question even more sharply, because it asks what happens when the inhale finally ends. If dark energy keeps weakening, the universe doesn't expand forever. If dark energy strengthens, it might tear itself apart. If dark energy stays exactly constant, space drifts into a slow, cold death. The fate of everything you've ever known, everyone you've ever loved, every star, every galaxy, every atom in existence, depends on which of these scenarios turns out to be true. Right now, scientists genuinely don't know which one is coming. The classical scenario was called the Big Freeze. With a steady cosmological constant pushing space apart, galaxies drift farther and farther from each other. New star formation slows as gas spreads too thin. Existing stars burn out. Black holes evaporate over impossibly long timescales. Eventually, the universe becomes a vast, dim, frozen sea of nothing. No light, no motion, no structure, just a perfect, silent emptiness extending forever. That used to be the boring, depressing default ending. Now it might be the optimistic one. The Big Rip is much worse. If dark energy turns out to be the phantom variety, growing stronger over time, expansion accelerates beyond any physical limit. First, galaxy clusters get torn apart, then individual galaxies, then solar systems, then planets, then stars, then the atoms that make up everything. In the final fraction of a second before the rip, the very fabric of space stretches faster than the speed of light, ripping particles into dissociated chaos. Some models put this catastrophe as far away as a few 100 billion years. Others suggest it could happen in as little as 20. Then there's the Big Crunch, or, as the recent DESI data hints at, the Big Collapse. If dark energy is weakening fast enough, expansion will eventually halt, then reverse. Galaxies will start falling toward each other instead of drifting apart. Over many billions of years, the universe contracts, galaxy clusters smash together, stars collide. Eventually, all matter is crushed back into a single point of infinite density, or, in the bouncing models, into a state that triggers another rebound. Either way, our cosmic chapter ends. The terrifying part is how the same dataset, the same DESI release, contains hints of all three futures, depending on which assumptions you make. The phantom phase points to a rip, the quintessence phase points to a crunch. A constant cosmological term still allows for the freeze. The data is genuinely ambiguous, and the future of everything hinges on better measurements. The newest analysis, published in late 2025, suggested an ominous tilt, a 93.8% preference for a future transition into an anti-de Sitter space, which may ultimately lead to a cosmological collapse of our universe. Translation: the math is starting to favor the crunch. Most cosmologists urge caution. A 93% preference is not the same as 5 sigma certainty. The data could shift again. New observations could swing the balance back to a steady cosmological constant. Statistical fluctuations have killed many promising signals before, but the fact that respected physicists are now openly modeling a future cosmic collapse, where space itself contracts and burns away every structure, is a remarkable shift. Just 20 years ago, the Big Crunch was widely considered impossible. Now it's back on the table, quietly, with serious researchers and solid data behind it. Whatever the answer, the universe seems determined to make us question our place in it. Every assumption gets stretched, every certainty gets challenged, every safe model gets shaken, including the model that defines our nearest cosmic landmark, the Milky Way itself, because there's something strange about our galaxy's motion through space, something that doesn't quite fit the predictions. And it might be tied to the same mystery that's twisting the rest of the cosmos. Earth is moving. Right now, you're spinning at about 1,000 miles per hour as the planet rotates. You're orbiting the Sun at 67,000 miles per hour. The Sun itself is dragging us through the Milky Way at over 450,000 miles per hour. And the Milky Way as a whole is hurtling through space at roughly 1.3 million miles per hour, relative to the cosmic microwave background. That last number is where things get strange. Astronomers have measured this motion very carefully. The cosmic microwave background, the leftover light from the Big Bang, fills the sky at a nearly uniform temperature, but not perfectly uniform. There's a tiny pattern called the dipole. One side of the sky looks slightly warmer than the other. The reason is simple. We're moving toward the warmer side. The motion compresses the wavelengths of light coming from that direction, making them slightly hotter. The opposite side gets stretched, making it slightly cooler. By measuring the dipole, scientists can calculate exactly how fast we're moving and which way we're going. The standard model predicts that this dipole, caused by our motion, should match other dipoles in the sky. For example, the distribution of distant quasars and radio galaxies should also show a similar lopsidedness, since their light is shifted by our motion in the same way. The two dipoles don't match. The dipole measured in the cosmic microwave background gives one answer. The dipole measured from quasars gives a different one. The mismatch is large enough to be a genuine puzzle. Either we're moving faster than the cosmic microwave background suggests, or there's something else creating an additional asymmetry in the universe. Something tilting matter slightly in one direction. This is called the cosmic dipole anomaly. It's been observed by multiple teams using different telescopes with different methods. The result keeps coming back the same way. The two dipoles disagree, and like the Hubble tension, the gap doesn't shrink with better data. If the disagreement is real, it has profound consequences. It means the universe has a preferred axis, a direction where matter is slightly more concentrated. The cosmological principle, the assumption that the cosmos looks the same in every direction, would be violated, not just by lumpy local structures like voids, but at the very largest scales we can observe. Some researchers have suggested this dipole could be tied to the KBC void. If our local region is asymmetrically positioned relative to the surrounding cosmic structure, the gravitational pull from one side would be stronger than the other. That extra pull would add to our motion, creating the mismatch we observe. The void wouldn't just bias our expansion measurements, it would bias our perception of the cosmic dipole too. Others have suggested even stranger explanations. Maybe the universe really does have a preferred direction baked in from the moment of creation. Some early universe theories allow for slight anisotropy at birth, an initial axis that gets preserved as space expands. If true, this would be a fundamental property of the cosmos, not a local fluke. Either explanation breaks the standard picture. Either we live in a uniquely strange location, or the universe itself isn't symmetric. What makes the cosmic dipole mystery so unsettling is that it touches almost every other anomaly we've discussed. The Hubble tension, the local void, the CMB cold spot, the strange, angular alignments. All of them might be threads of the same tapestry. A tapestry where the universe is trying to tell us something we haven't been ready to hear. That something gets even stranger when you look at the very edges of cosmic time. Because the deeper we look, the more it seems that the universe was already complex, already organized, already busy, almost from the moment it began. Cosmologists used to be confident about how the universe grew up. Hot Big Bang, nearly featureless plasma, slow cooling, first stars after a few 100 million years, galaxies forming over billions of years through gradual mergers, black holes building up from stellar deaths, accumulating mass over cosmic time, a clean, orderly developmental sequence. That timeline is now in shambles. We've already talked about the impossible early galaxies that the James Webb Space Telescope keeps finding. Massive, mature structures that shouldn't have had time to form. But the problem isn't just galaxies, it's also black holes and quasars. And the chemistry of the early universe. Quasars are the brightest objects in the cosmos. They're powered by supermassive black holes, ones with masses millions or billions of times that of the Sun, gulping down matter at incredible rates. Standard models predict that black holes this large need many hundreds of millions, even billions of years to grow. Stellar deaths produce small black holes. Mergers slowly accumulate them into bigger ones. Accretion adds mass over enormous timescales. So when astronomers find a quasar powered by a billion solar mass black hole at the dawn of the universe, just 600 or 700 million years after the Big Bang, the math falls apart. The black hole is too big to have formed in the time available. Even if you start it as a big seed and feed it constantly at the maximum allowed rate, the equations say it shouldn't be that massive yet. These objects aren't rare. Webb and other observatories have found many of them. The early universe was full of them, which means the way black holes form must be different from what we thought. Perhaps they were born already enormous, through some exotic process. Direct collapse of giant gas clouds. Primordial black holes seeded from the Big Bang itself. Some unknown channel of structure formation. The same problem appears in cosmic chemistry. The first stars were supposed to be made almost entirely of hydrogen and helium, the only elements that existed shortly after the Big Bang. Heavier elements like carbon, oxygen, and iron should have taken many generations of stars dying and recycling material to build up. Yet observations of the earliest galaxies show measurable amounts of heavy elements existing far too soon. The universe seems to have polluted itself with metals faster than the standard models allow. Pulling this all together, a strange picture emerges. The universe didn't gradually mature. It seems to have arrived already partially developed. Galaxies, black holes, heavy elements, all present, all functioning, all flourishing, when the cosmos was barely a fraction of its current age. This timeline crisis ties back to our central mystery. If the universe expanded differently than predicted, if the rate of cosmic stretching was once different from what we calculate, then the time available for these structures to form might have been longer. A weakening dark energy in the early universe could leave more time for things to grow. A different gravity in the early epochs could speed up structure formation. The strangely full early cosmos might be another fingerprint of physics behaving in ways we haven't yet understood. Or it might be something even more radical. Some researchers have suggested that the standard cosmic timeline simply isn't right, that the universe is older than 13.8 billion years, possibly significantly older. New analyses using a different distance method have produced age estimates ranging up to 26 billion years. Most cosmologists reject these numbers, but they exist. They're not fringe, and every new data anomaly makes them slightly harder to dismiss. The universe we live in might not be the universe we think we live in. Older, lumpier, weirder, less symmetric, and shaped by forces we still don't fully understand. And the next clue makes the strangeness personal, because there's a chance, a small but real chance, that everything we observe might actually be a kind of mirror, reflecting something far stranger underneath. Imagine looking at a credit card. On the surface, you see what appears to be a three-dimensional image, sometimes a bird, sometimes a logo, shifting as you tilt the card. But the image isn't really three-dimensional. It's a flat pattern of light and shadow, encoded on a two-dimensional surface that your brain interprets as having depth. That trick has a name. It's called a hologram. In 1997, a physicist named Juan Maldacena proposed that the entire universe might work the same way. The idea is called the holographic principle. It comes out of work on black holes by Stephen Hawking and Jacob Bekenstein, who showed something deeply strange. The amount of information that can be stored inside a black hole isn't determined by its volume. It's determined by the surface area of its event horizon. The two-dimensional boundary, not the three-dimensional interior, is what counts. If this is true for black holes, some physicists wondered, why not for the universe as a whole? Maybe the cosmos we experience as three-dimensional is actually a projection of information stored on a distant two-dimensional boundary. The depth, the volume, the sense of space stretching out around us, all of it could be encoded on a flat surface, like the image on a credit card hologram. The math behind this idea is not vague speculation. It's been worked out in detail in specific contexts, particularly something called AD-CFT correspondence. In those models, a three-dimensional gravitational universe is mathematically equivalent to a two-dimensional quantum field theory living on its boundary. Both descriptions give the same answers. Both are equally real. The holographic principle works. The puzzle is whether our universe specifically is one of these holographic systems. There's no smoking gun proof yet, but there are tantalizing hints. One hint comes from the Hubble tension itself. Several theorists have suggested that the mismatch between early and late universe expansion rates might naturally appear in holographic models. The way information leaks across the cosmic boundary could subtly shift expansion measurements over time. The weakening dark energy seen in DESI data might be another signature. If dark energy is fundamentally tied to the entropy of the cosmic horizon, its strength would change as the universe grows. The cosmological constant wouldn't be constant, because its value would depend on how much information the boundary contains at any given moment. There's even an experimental test underway. A device called the holometer, built at Fermilab, looked for tiny jitters in space-time that would be expected if reality were pixelated at the smallest scales. The first runs found nothing definitive, but more sensitive successors are now being designed. If the universe is truly holographic, somewhere down at the Planck scale, space itself should not be smooth. It should be grainy, pixelated, made of discrete bits of information. The philosophical weight of this idea is enormous. If you and everyone you love are essentially patterns of information encoded on a distant boundary, then the deepest truth about reality is something like a vast cosmic computer. Space, time, matter, energy, all of it would be emergent, none of it fundamental. The universe would not be a place, it would be a calculation. This connects back to entropic gravity, to the bouncing universe, to every other strange cosmic mystery. They all share a common theme. The universe might not be made of stuff. The universe might be made of information, and that information might be processed, stored, and reorganized in ways that make our most basic intuitions about space and time look like cartoons. If this is right, then solving the cosmic expansion mystery isn't just about finding a better equation for dark energy. It's about decoding the rules of the simulation, or the hologram, or whatever metaphor turns out to fit best. And that brings us face to face with the strangest possibility of all, a possibility that some respected scientists now openly take seriously, a possibility that suggests the entire universe, from the Big Bang to the last star, might be running inside something else entirely. In 2003, an Oxford philosopher named Nick Bostrom published a paper that changed how serious thinkers talk about reality. The paper asked a simple question. If any civilization ever became advanced enough to simulate conscious beings inside a computer, and if that civilization ran many such simulations, then statistically, the odds that we ourselves are living in one of those simulations would be overwhelming. Not zero, not maybe, overwhelming. The argument is uncomfortable. It's also harder to dismiss than most people expect. Think about how computer graphics have evolved. 40 years ago, video games were blocky pixels and crude beeps. Today, virtual environments include realistic physics, ray-traced lighting, and characters whose faces respond to emotional cues. In another century, simulations could include sensory experiences indistinguishable from real life. In 1,000 years, the gap between simulated and physical reality might close completely. If that ever happens to any civilization, anywhere in the universe, the population of simulated minds would vastly outnumber the population of biological minds. By sheer numbers, any consciousness picked at random would more likely be a simulated one. This idea sounds like science fiction, but several anomalies in our universe have been pointed out as suspicious by physicists who genuinely consider the possibility. The fine-tuning of physical constants, the mathematical elegance of natural laws, the fact that quantum mechanics seems to load reality at the moment of observation, like a video game rendering only what the player can see. Even the apparent pixelation of space at the Planck scale could be interpreted as evidence of an underlying computational substrate. The Hubble tension and the weakening dark energy fit into this picture in unsettling ways. If our universe is a simulation, the people running it might be updating the rules, patches, software upgrades, tweaks to make the system more efficient as the simulated cosmos grows more complex. A shift in dark energy could be a reduction in computational load. The mismatch between early and late universe expansion could be the result of changes in how the simulation processes different scales of physics. To be clear, no respected physicist claims this is the most likely explanation. The simulation hypothesis remains philosophy, not science. There's no direct evidence, probably never will be. A simulation good enough to fool us would be good enough to hide its own seams. Still, some clever experimentalists have proposed tests. They look for signatures, that might leak through if reality were running on a discrete computational grid. One experiment involves searching for tiny anisotropies in the spectrum of high-energy cosmic rays. If space were a 3D lattice, the rays would interact slightly differently depending on direction. So far, no clear lattice signatures have appeared. But the searches continue. The deeper point is not that we definitely live in a simulation. It's that the universe behaves in ways that make the question reasonable to ask. Information seems fundamental. Reality seems pixelated at the smallest scales. The laws of physics seem fine-tuned. Cosmic expansion seems to follow rules that shift over time. None of this proves anything. All of it makes the simulation hypothesis at least as plausible as a multiverse, a holographic boundary, or a cyclic bounce. And here's the unsettling part. Each of those hypotheses, if true, would mean our intuitions about reality are wrong in some fundamental way. We don't know which one is correct. We only know that the universe keeps refusing to fit inside the simple, comforting picture our textbooks gave us. Step back from the philosophy, though. Strange ideas aside, there's a much more concrete clue hiding in the data. A clue from the very early moments after the Big Bang. The kind of moment that lasted less than a second, but reshaped the entire cosmos. In the first tiny fraction of a second after the Big Bang, something extraordinary happened. The universe expanded faster than the speed of light, not because anything was moving through space at that speed, but because space itself was stretching, and space isn't bound by the same speed limit as objects within it. In a window of time so short it's almost incomprehensible, the universe doubled in size about 90 times. A patch smaller than a proton ballooned into something larger than a grapefruit. This sudden, violent stretching is called cosmic inflation. Inflation explains a lot of things our standard model otherwise can't. Why the universe looks so smooth on large scales. Why the cosmic microwave background has nearly the same temperature in every direction. Why space appears geometrically flat, instead of curved like a sphere or saddle. Without inflation, none of these properties would make sense. The problem is that nobody knows what caused inflation. We have no direct evidence of the field that powered it. We have no laboratory test that confirms its mechanism. Inflation is a beautifully successful theory, built on top of a giant unknown. Multiple versions exist: slow-roll inflation, eternal inflation, hybrid inflation, new inflation. Each predicts slightly different signatures. Each requires slightly different physics. Some versions naturally produce a multiverse of bubble universes. Others predict that inflation never truly ends, and that new universes are still being born somewhere out beyond our cosmic horizon. What's startling is how the modern Hubble tension might tie into the inflation story. If inflation produced extra energy or extra particles that haven't been accounted for, it could shift the early universe predictions for the expansion rate. Some cosmologists have proposed something called early dark energy, a brief surge of dark energy in the moments after inflation, which would naturally raise the predicted Hubble constant from the lower number to the higher one. It would close the gap. The early dark energy idea is controversial. It requires fine-tuning of new physics. Critics say it's an elegant fix that creates more problems than it solves. Other researchers point out that it might actually emerge naturally from string theory, which contains many fields that could play exactly that role. There's also a deeper mystery hiding in inflation itself. The theory predicts that the smallest quantum fluctuations during the inflationary period got stretched into the seeds of every galaxy and cluster we see today. Those tiny ripples grew over billions of years into the entire cosmic web. We can read them in the cosmic microwave background. The match between predicted and observed fluctuation patterns is one of the great triumphs of modern cosmology. But the match isn't perfect. There are statistical anomalies in the cosmic microwave background that don't quite fit the simplest inflation models. The amplitude of certain fluctuations is slightly off. The distribution of temperature variations across the sky shows hints of patterns that pure quantum noise shouldn't produce. The universe seems to remember something, some fingerprint from the inflationary epoch that our equations haven't fully decoded. If the fingerprint is real, it could rewrite our understanding of the very first moment of the cosmos. Maybe inflation wasn't a single, smooth episode. Maybe it had multiple phases, like a person who hesitates before sprinting. Maybe it was driven by exotic physics involving extra dimensions, hidden sectors, or fields connected to dark matter and dark energy. Each possibility produces slightly different predictions. Each could leave a different signature. The next generation of cosmic microwave background telescopes is now hunting for these signatures. The most precious one is something called primordial gravitational waves, ripples in space-time produced by inflation itself. If they're found, they would be direct evidence of physics happening near the beginning of time. They would also constrain which version of inflation actually occurred. So far, none have been detected, but the search continues, and every new measurement narrows the possibilities. The truth is hiding in the noise. Somewhere in those tiny fluctuations is the answer to how everything began. Particle physics has a haunted house. It's called the desert. For nearly a century, theorists have predicted that the laws of nature should contain a rich landscape of fundamental particles, stretching from energies we can probe in our colliders all the way up to the unimaginable scale of quantum gravity. New physics, supersymmetry, hidden forces. The math practically demands it. The Large Hadron Collider, the most powerful particle accelerator ever built, has spent over a decade hunting for those predicted particles. It found one, the Higgs boson, in 2012. Since then, despite running experiments at unprecedented energies, it has found nothing else. The desert stretches on. The expected new particles are missing. This silence is one of the great unsolved problems of modern physics, and it ties directly into our cosmic expansion mystery in ways that aren't obvious at first. Many proposed solutions to the Hubble tension and the dark energy puzzle involve new particles or new fields, light bosons that interact weakly with normal matter, sterile neutrinos that don't engage with the standard forces, axions that could form a kind of fuzzy dark matter. Each new theory adds new particles. Each one predicts that, if you build a sensitive enough experiment, you should be able to detect them. The detectors keep coming up empty. Underground experiments hunting for dark matter particles have grown 1,000 times more sensitive over the last 20 years. They sit in old mines, shielded from cosmic rays, waiting for a single dark matter atom to brush against an atomic nucleus. The signal would be tiny, a faint flash, a whispered nudge. After billions of dollars and millions of detector hours, the whisper has not arrived. Either dark matter is much weirder than we thought, or it isn't there at all. The same pattern holds for axion searches, light boson searches, and exotic neutrino searches. All ambitious, all increasingly sensitive, all silent. There's something deeply uncomfortable about this. The universe seems to demand new physics to explain its largest scale behavior, yet it refuses to show us the new physics in any laboratory experiment. As if the rules that govern the cosmos and the rules that govern the lab don't talk to each other. Some theorists think this means the new physics lives at energy scales we can't yet reach. Quantum gravity effects only matter at the Planck scale, far beyond any conceivable accelerator. If dark energy and cosmic expansion involve gravitational physics at that scale, no earthbound experiment will ever directly test them. We could be permanently cut off from the answer. Others suggest the missing particles aren't missing at all. They're hiding in plain sight. Modifications to gravity, like Mond or entropic gravity, naturally avoid needing new particles. The cosmos behaves the way it does not because of invisible substances, but because the rules themselves are different from what we wrote down. A third possibility is the most unsettling. Maybe there isn't a discovery to be made. Maybe the universe is genuinely strange in ways that don't reduce to neat particles or elegant equations. Maybe the puzzles in cosmology are pointing towards something that doesn't fit any of our current categories at all. Whatever the answer, the silence of the colliders is informative. The new physics, if it exists, is not the kind of thing we can simply build a bigger machine to find. It's hiding behind something, maybe behind the smallest scales we know, maybe behind the largest, maybe behind the very nature of measurement itself. That last possibility takes us into a stranger territory, because at the deepest level of reality, particles and waves blur into something that doesn't quite obey our intuitions, and the rules of that blur might be the missing key to the cosmic puzzle. There's a number in physics that should embarrass every theorist who has ever lived. It's the difference between what quantum mechanics predicts for the energy of empty space and what we actually observe. Empty space isn't really empty. According to quantum field theory, the vacuum is constantly fluctuating. Pairs of virtual particles flicker into existence and vanish before they can be detected. These fluctuations carry energy. We can measure their effects. They cause subtle shifts in atomic spectra. They produce a tiny, attractive force between very close metal plates, called the Casimir effect. We've tested these predictions in labs. They work. When you add up all the energy of all the virtual particles in a single cubic centimeter of empty space, the answer is enormous. By naive calculation, the energy density of the vacuum should be around 10 to the power of 120 times larger than what we observe in cosmology. That's not a typo. 1 followed by 120 zeros times too big. It's the worst prediction in the history of science. If the predicted vacuum energy were actually present in our universe, space would be expanding so fast that no atoms could form. No galaxies, no stars, nothing. Reality as we know it could not exist. Yet the actual vacuum energy is tiny, just enough to drive the gentle, accelerated expansion we observe, just enough to be dark energy. This catastrophe has been called the worst mystery in physics. Solving it would require explaining why nature manages to cancel out 120 orders of magnitude of vacuum energy almost perfectly, leaving only a tiny residual. No known mechanism does this. No standard model calculation produces the right answer. For a long time, the cosmological constant was assumed to be exactly zero, with the tiny observed value being some kind of measurement issue. Then the universe was discovered to be accelerating. Suddenly, dark energy was real, the constant was real, and the catastrophe became unavoidable. Now, physicists had to explain not just why almost all the predicted vacuum energy disappears, but why a small specific fraction survives and is responsible for cosmic expansion. The new DESI data makes the puzzle even worse. If dark energy is changing over time, then whatever cancellation mechanism nature uses isn't fixed. It's dynamic. It evolves. It adjusts the leftover vacuum energy as the universe ages. No model in standard physics naturally produces this kind of behavior. Several creative ideas have been proposed. Maybe there's a hidden symmetry that almost perfectly cancels vacuum energy, with tiny braking effects producing the residual we observe. Maybe vacuum energy is connected to a slowly rolling field, a kind of cosmic pendulum that releases energy over time. Maybe there's a deep connection between the vacuum and gravity that we haven't yet uncovered, where most of the vacuum energy doesn't gravitate at all. Each idea has problems. Each requires assumptions that aren't supported by independent evidence. The vacuum catastrophe remains an unsolved mountain in the middle of physics, blocking the path to any complete theory of the cosmos. What this teaches us is that our understanding of empty space is still primitive. We don't know what the vacuum really is. We can describe its effects. We can measure its fluctuations. We cannot explain why it has the properties it does. And until we can, we won't truly understand dark energy, cosmic expansion, or the ultimate fate of the universe. The vacuum mystery touches on something almost philosophical. It suggests that nothingness isn't really nothing. It's a complex, structured, fluctuating environment whose deepest properties we don't yet grasp. And from that nothingness, somehow, everything we know emerged. The next chapter takes that idea even further, because if the vacuum is mysterious, the boundaries between vacuum and matter, between empty space and the things that fill it might be more porous than we ever imagined. For more than a century, the speed of light has been treated as the ultimate cosmic limit, 300 million meters per second, constant, universal. The rate at which information, gravity, and electromagnetic radiation can travel through any vacuum, anywhere, at any time. Einstein's relativity is built on this foundation. So is most of modern cosmology. But what if it's not actually constant? A handful of physicists have proposed a controversial idea called variable speed of light cosmology. The idea is exactly what it sounds like. Maybe in the very early universe, light traveled faster than it does today. As the cosmos aged, the speed of light slowly decreased to its current value. If true, this would have enormous consequences for almost every problem in cosmology. A faster early speed of light would explain why distant regions of the universe look so similar to each other. Light from one side of the cosmos could have crossed the entire visible universe in the early epochs, equilibrating temperatures and densities. This would solve some of the same problems that inflation solves, but through a completely different mechanism. It would also provide more time for early structures to form, potentially explaining the Webb telescope's massive early galaxies. Most physicists are deeply skeptical. The constancy of the speed of light is one of the most carefully tested principles in science. Lab experiments routinely measure it with breathtaking precision. Astronomical observations from across cosmic distances all confirm the same value. If it were changing, we'd expect to see signatures, and the standard observation tools haven't found them clearly. Yet the idea refuses to die. Recent analyses have shown that variable speed of light models can match certain cosmic observations, as well as inflation, sometimes better. They naturally accommodate things like the Hubble tension, because the relationship between time, distance, and expansion all depend on what value of the speed of light you assume in the early universe. There's a related, more speculative possibility. What if other fundamental constants also drift? The fine structure constant, which controls how strongly light interacts with matter, has been the subject of careful searches for variation. Some studies have hinted at tiny shifts across cosmic time. The hints aren't conclusive, but they aren't dismissed either. If the fine structure constant truly varies, then the basic atomic physics that makes stars and chemistry possible would be different in different epochs. This brings us back to a broader theme. The universe might not be running on a fixed set of laws. Different epochs might have different physical constants. Different regions of space might have slightly different rules. The cosmos could be more like a developing organism than a rigid mechanism, growing, changing, evolving its own physics as it ages. If that's true, then the cosmic expansion mystery isn't just about dark energy or dark matter. It's about a universe whose very rules are in flux. The early measurement and the late measurement don't agree because they aren't measuring the same physics. The cosmos itself is rewriting the laws underneath us, and we're trying to fit the changing reality into a framework that assumes everything stays the same. This idea sounds heretical. It also has historical precedent. Many established physical principles have been revised or generalized as new observations came in. The shift from Newton to Einstein, the shift from classical to quantum mechanics, the discovery that the universe isn't static but expanding. Each revolution required scientists to abandon assumptions they had treated as bedrock. We may be on the edge of another revolution. The signals are everywhere. The Hubble tension, the weakening dark energy, the early massive galaxies, the desert in particle physics, all of them might be telling us the same thing. The rulebook isn't done being written, and the next mystery suggests that the rulebook might have to include something even stranger, a property of the universe that has no name, no clear cause, and no place in any current theory. Look at the universe today, and you find something suspicious. The amount of dark energy, the amount of dark matter, and the amount of normal matter all happen to be of comparable magnitude. They're not equal. Dark energy dominates at about 70%. Dark matter sits around 25%. Normal matter trails behind at 5%. But across the unimaginable range of values these quantities could in principle have, the fact that they're all within the same ballpark is strange. This is called the cosmic coincidence problem. The strangeness deepens when you consider how these quantities evolve. Dark energy doesn't change with the expansion of space. In the simplest models, matter dilutes as space expands. So, in the early universe, matter dominated overwhelmingly. In the far future, dark energy will dominate overwhelmingly. We happen to live at the precise moment when their contributions are roughly balanced. Why now? Why are we here, at this unique cosmic moment, when the components of the universe happen to be comparable? It's like walking into a room and finding 3 different hourglasses, each emptying at a different rate, all happening to show the same amount of sand at the moment you arrive. Several explanations have been proposed. The anthropic principle says we observe this coincidence because it's the only era when stable galaxies and stars can exist long enough for complex life to evolve. If we existed too early, gravity from matter would have prevented stable structures. Too late, dark energy would have ripped everything apart before life could form. Only this narrow window allows observers like us. So of course we find ourselves here. But many physicists find the anthropic explanation unsatisfying. It works as a filter. It doesn't explain a mechanism. It tells us why we observe the universe at this moment without telling us why the universe is structured this way at all. The newer DESI data adds another wrinkle. If dark energy is actually evolving, then the coincidence might not be as suspicious as it first looks. A dark energy that grows and shrinks over time would naturally produce moments where its strength matches the matter density. The match wouldn't be a 1 in a trillion accident. It would be a normal feature of cosmic evolution. We'd just happen to live during one of those phases. Some theorists go further. They propose that the cosmic coincidence isn't really a coincidence. There might be a deep connection between dark matter and dark energy. Maybe they're 2 faces of the same underlying field. As one strengthens, the other weakens. Their balance point might be set by the geometry of the universe itself, like water finding its level. If this is right, then the very structure of the cosmos is self-regulating. The components adjust themselves to maintain a kind of cosmic balance, and observers like us emerge in eras when that balance allows complex chemistry. The fine-tuning isn't accidental, it's structural. There's also the possibility that the coincidence reflects something even more fundamental. Some interpretations of holographic cosmology suggest that dark matter and dark energy both emerge from the entanglement structure of the universe. As that structure evolves, both quantities change in correlated ways. The match between them is dictated by the holographic boundary, not by random chance. What unites all these ideas is a common conclusion. The universe is not a random arrangement of independent quantities. It's an interconnected whole, with deep relationships between its different components. We don't yet understand those relationships. But every cosmic anomaly, including the cosmic coincidence, hints that the connections are real. That theme of hidden connections runs through cosmology like a thread. We've seen it in dark energy. We've seen it in inflation. We've seen it in quantum mechanics. And now we're about to see it in the most literal possible way. In the way information might be quantum entangled across the entire universe. Quantum entanglement is one of the strangest phenomena ever discovered. Einstein himself called it spooky action at a distance. When 2 particles become entangled, their properties are connected in a way that doesn't depend on the distance between them. Measure one, and the other instantly takes on a correlated state. No signal travels between them. No force acts. The connection is woven into the very fabric of quantum mechanics. For decades, entanglement was treated as a curious feature of microscopic systems, useful for quantum computers, maybe useful for quantum cryptography, largely irrelevant to the big questions of cosmology. Then a remarkable theoretical insight emerged. What if entanglement isn't just a property of particles? What if it's the secret ingredient that builds space-time itself? This idea grew out of work on black hole physics in the early 2010s. Researchers showed that the geometry of certain spacetimes can be reconstructed from patterns of quantum entanglement. The more entangled two regions of a quantum system are, the closer together they appear in the corresponding spacetime. Distance, it turns out, might literally be a measure of how strongly two parts of the universe are quantum correlated. If this is right, then space itself is not a fundamental backdrop. Space is emergent. It rises out of the entanglement structure of an underlying quantum system, the way temperature rises out of the average motion of molecules. There's no preferred spatial container in which the universe exists. The container itself is built from quantum information. This changes everything about how we think of cosmic expansion. If space is emergent from entanglement, then the expansion of space is really the rearrangement of entanglement patterns. As the universe ages, the way information is distributed shifts. Distances grow because connections weaken. Galaxies move apart because the underlying quantum links between them become more diluted. In this picture, the Hubble tension might reflect the difference between two ways of measuring entanglement evolution. The early universe measurement looks at the distribution of entanglement when the cosmos was young and dense. The late universe measurement looks at the distribution today, after billions of years of dilution. The two values might disagree because the simple equations connecting them don't fully capture how entanglement shifts over cosmic time. Dark energy fits naturally into this framework as well. Some theorists have proposed that dark energy is an entropic effect of entanglement at the cosmic horizon. As the universe expands and information becomes more spread out, the entanglement structure produces an effective pressure that drives further expansion. The cosmological constant is replaced by a dynamic property of cosmic information. This view also offers a possible explanation for the coincidence problem. Dark matter and dark energy might both emerge from different aspects of the entanglement web. Their balance is set by the structure of that web at any given moment. The coincidence between them isn't random. It's a natural consequence of how information is organized. There are concrete experimental possibilities. If space really is built from entanglement, then very precise measurements of quantum systems should reveal subtle gravitational effects that don't fit standard expectations. Some teams are working on tabletop experiments designed to test exactly this. So far, no clear deviation has been found, but the technology is improving rapidly. The deeper implication is staggering. If entanglement is the fundamental glue of reality, then the universe is connected in ways we cannot directly perceive. Every part of the cosmos is woven into every other part, every galaxy, every star, every atom in your body, all linked through the underlying quantum web that gives rise to space itself. That web extends to the farthest reaches of the visible universe, and maybe beyond, to regions we have never seen, to structures we cannot detect with any telescope, to the very edges of reality, where the next mystery lives. Hidden behind the band of stars and dust that forms the Milky Way, in a region of sky we can barely see through, lies something colossal. Astronomers call it the Great Attractor. It is the gravitational center of our local cosmic neighborhood, and it's pulling the Milky Way, along with thousands of other galaxies, toward itself at speeds of nearly 1.5 million miles per hour. The Great Attractor was first noticed in the 1970s, when astronomers measured the velocities of nearby galaxies and found that they were not moving randomly. Instead, they were all drifting toward a single direction in the sky. The pull was real. The cause was hidden. Whatever was creating this gravitational tug was located behind the dust of our own galaxy, making it almost impossible to study directly. For decades, astronomers thought the Great Attractor was a particularly massive cluster of galaxies. They pointed radio telescopes and X-ray telescopes through the cosmic dust, slowly building a picture of what lay behind the obscuring band. Eventually, they identified the Norma cluster as the central anchor. But there was a problem. The Norma cluster wasn't massive enough to produce the observed gravitational pull. There had to be more, something even bigger, something farther. In 2014, a team led by Brent Tully announced the discovery of an enormous structure called Laniakea. The name comes from Hawaiian, meaning immeasurable heaven. Laniakea is a supercluster 500 million light-years across, containing about 100,000 galaxies. The Milky Way is one of them. The Great Attractor sits near the center of Laniakea, and the entire supercluster is being pulled by it. Even Laniakea isn't enough. Beyond it lies an even larger structure called the Shapley concentration. This is the densest known concentration of galaxies in the nearby universe, and it appears to be exerting its own gravitational influence on Laniakea. Together, the Great Attractor, Laniakea, and the Shapley concentration form a hierarchy of cosmic pulls, each larger than the last. Now here's where this connects to our central mystery. These massive structures shouldn't be possible inside the standard model of cosmology, or at least not on these scales. The cosmological principle says structures larger than a few 100 million light-years shouldn't exist in significant numbers. Yet Laniakea is 500 million light-years across, and it's part of an even larger pattern. The Shapley concentration extends the connected structure to nearly 1 billion light-years. The standard model can produce some large-scale structure, but the consistency and scale of what we observe pushes the limits. Combined with the KBC void, the Great Walls, and other oversized structures, the picture is one of a universe far lumpier and more dramatic than predicted. The Great Attractor also affects measurements of cosmic expansion. The Milky Way's motion toward Laniakea adds a velocity component to everything we observe. Distant galaxies appear to be moving slightly differently because of our own bulk motion. Cosmologists try to subtract this effect, but the corrections aren't perfect. Some researchers have argued that residual local motions could be biasing our measurements of the Hubble constant in subtle ways that haven't been fully accounted for. There's also a deeper question. What's pulling the Shapley concentration? Beyond Shapley, are there even larger structures? The deeper we look, the bigger the universe seems to organize itself. The structures we see might just be the tip of a vast cosmic iceberg, with the real architecture extending far beyond our current observational reach. If the universe really is organized into larger and larger nested structures, then our standard picture of a smooth, evenly expanding cosmos is wrong at every level. Local motions matter, bulk flows matter, the lumpiness matters, and the Hubble tension, the dark energy puzzle, the coincidence problem, all might be downstream effects of a cosmic architecture we don't yet fully understand. That hidden architecture could go even deeper, because the next mystery suggests that what we call empty space might not be empty at all. Take all the galaxies in the universe, every cluster, every supercluster, every void, plot them in 3 dimensions. What you get isn't a random scatter of points. It's a delicate, branching structure, long filaments of galaxies stretching for hundreds of millions of light-years. Sheets of galaxies forming vast cosmic membranes. Empty voids in between, where almost nothing exists. The whole pattern looks like a giant spider web, woven across the entire visible universe. This is the cosmic web, and it's one of the most beautiful and important discoveries in astronomy. The cosmic web exists because of a process called gravitational instability, tiny density fluctuations. In the very early universe, the same ones we see imprinted on the cosmic microwave background, grew over billions of years. Slightly denser regions pulled in more matter, slightly emptier regions lost what little they had. Over time, this amplification turned the smooth early cosmos into the lacy, structured cosmos we observe today. What's astonishing is how predictable the web's main features are. Computer simulations starting from cosmic microwave background measurements can reproduce the general shape of the modern cosmic web with remarkable accuracy. The locations of clusters, the lengths of filaments, the sizes of voids, The simulations and observations match well, but not perfectly. The deeper you look, the more the discrepancies grow. Some specific cosmic structures are bigger or denser than the simulations predict. The Hercules Corona Borealis Great Wall is so large it shouldn't exist in any standard model. Certain voids are too empty. Certain clusters are too well formed for their cosmic age. The big picture matches, the fine details don't. Even more puzzling, the cosmic web seems to influence cosmic expansion itself. Light traveling through dense filaments takes a slightly different path than light traveling through empty voids. Time runs at different rates in different parts of the web. Photons gain or lose energy as they cross density variations. These effects bias every measurement we make of the distant universe. The integrated Sachs-Wolf effect is one example. Photons from the cosmic microwave background gain energy when they fall into density wells, then lose it again when they climb out. In a perfectly static universe, the gain and loss cancel out. In an expanding universe with dark energy, they don't cancel exactly. Light gets a small net boost or drag depending on the structures it crosses. Astronomers have measured this effect, and it broadly matches predictions. But the match isn't perfect, and small discrepancies might be telling us something about how dark energy actually behaves. There's also a deeper philosophical point. The cosmic web tells us that the universe is fundamentally connected. No region exists in isolation. Every galaxy sits inside a filament. Every filament is connected to others. The web binds the cosmos together in a single, vast network of matter and gravity. This connectivity might be more important than we realize. If entanglement and emergent space are real, then the cosmic web could be a visible echo of a deeper, invisible web of quantum information. The filaments and voids we see might trace patterns in the underlying entanglement structure. The architecture of the universe at large scales would mirror the architecture of reality at the smallest scales. If we could read this echo correctly, we might find answers to questions that seem unanswerable today. Why does dark energy have the value it does? Why is the cosmic expansion mysterious? Why are there structures at scales we can't quite explain? The web could be the universe's way of writing its own physics in a form we can almost understand. For now, the web remains a mystery in its own right. We can describe it, we can simulate parts of it. We cannot fully explain why it has the exact features it does. And every new survey adds new puzzles to the picture. Just like every new cosmological measurement adds new tensions to our understanding of expansion. The latest puzzle, though, comes from the most recent and ambitious survey ever conducted. It's not just about cosmic expansion, it's about whether the laws of physics themselves are different in different parts of the cosmos. The fine structure constant is one of the most important numbers in physics. It's about 1/137, and it controls how strongly light interacts with matter. Change this number even slightly, and atoms wouldn't form the same way. Chemistry wouldn't work the same. Stars wouldn't shine the same. Life, in any form we'd recognize, would not exist. For most of the 20th century, physicists assumed this constant was exactly that, a constant, the same value everywhere in the universe, at every moment in cosmic history. Then a team led by John Webb at the University of New South Wales started looking at light from distant quasars. Quasars are the bright cores of ancient galaxies, billions of light years away. The light they emit takes that long to reach us, which means we're seeing the universe as it was long ago. By analyzing the light, scientists can read off the values of physical constants in the era when the light was first emitted. What Webb and his colleagues found was not what anyone expected. The fine structure constant appeared to be slightly different in different parts of the sky. In one direction, it seemed to have been slightly smaller in the past. In the opposite direction, it seemed to have been slightly larger. The variation was tiny, just a few parts per million, but it was systematic. It pointed to a possible cosmic dipole in the laws of physics themselves. If real, this would be a discovery of extraordinary magnitude. It would mean that the universe is not isotropic in its physical laws. Different parts of the cosmos would have slightly different rules. The fine structure constant would have a preferred axis, just like the cosmic microwave background dipole and the quasar dipole we discussed earlier. The result has been controversial. Some teams have tried to reproduce it and failed. Others have found similar patterns in different datasets. The signal is at the limit of current measurement precision. It could be real. It could be a systematic error in how the analyses are done. The verdict is still genuinely uncertain. What's striking is that the alleged variation lines up with other cosmic anomalies. The direction of the fine structure dipole is roughly aligned with the direction of the Hubble tension dipole and the matter density dipole. If all these directions are pointing the same way, that's no longer a coincidence. It's a pattern, and the pattern suggests that the universe has a built-in axis, a preferred direction baked in at the deepest levels of physics. If the fine structure constant really does vary, then almost every assumption in cosmology needs revision. Distance measurements based on atomic spectra would have to be corrected. Star formation rates in distant galaxies would shift. The cosmic microwave background analysis itself might need rewriting. The Hubble tension could be partly explained by these corrections, though probably not entirely. Even more dramatically, a varying fine structure constant would force us to ask whether other constants vary too. The strength of gravity, the mass of the electron, the speed of light, all of these have been carefully tested for cosmic variation, and most show no clear evidence of change. But the precision is limited. Tiny variations could exist below current detection thresholds. The deeper question is what kind of universe would have changing constants? Theories of cosmic inflation, especially eternal inflation, naturally produce regions where constants take slightly different values. String theory landscapes contain many possible vacuum states, each with its own physical laws. If our universe samples different parts of such a landscape, then the constants we measure could depend on where in the cosmos we look. We don't yet have proof, but the hints keep accumulating. Each one is small. Each one could be dismissed individually. Together, they paint a picture of a universe whose physics might be more dynamic, more variable, and more mysterious than anything our textbooks describe. That dynamism might extend to one of the most extreme objects in the cosmos, an object whose very existence stretches the boundaries of what physics can describe. The black hole. Black holes are the most extreme objects in the universe, regions of space-time where gravity is so strong that nothing, not even light, can escape. They're the cosmic punctuation mark at the end of the most massive stars, and they sit at the centers of nearly every galaxy, including our own. For decades, they've been studied as exotic curiosities. Now, some physicists are beginning to wonder whether black holes might be at the heart of the cosmic expansion mystery itself. The connection comes from a theory called black hole cosmology. The basic idea is that the formation of black holes in the universe could be tied directly to the production of dark energy. As the universe ages and more stars collapse into black holes, the total dark energy content might increase in proportion. This would make dark energy not a fundamental property of empty space, but a side effect of cosmic structure formation. In 2023, a team analyzed observations of supermassive black holes inside ancient elliptical galaxies. They found that these black holes seem to grow over cosmic time, even when they're not actively accreting matter. The growth is correlated with cosmic expansion. The more space stretches, the more massive the black holes become. The team called this phenomenon cosmologically coupled growth. The implication, if confirmed, is staggering. Dark energy might literally come from black holes. Each time a star collapses into a black hole, a small amount of dark energy is added to the universe. As more black holes form, dark energy strengthens. Cosmic expansion accelerates. The universe is expanding because of its own contents, not because of some mysterious external force. The idea is not yet mainstream, It's been challenged by other groups who argue that the cosmologically coupled growth signal might be an artifact of how black hole masses are estimated. The data is genuinely ambiguous, and more observations are needed. But the framework offers something elegant. It connects the larger scale physics, cosmic expansion, with the most extreme local objects, black holes. It explains why dark energy might evolve over time, since black hole formation rates change over cosmic history. It even suggests a possible mechanism for the weakening dark energy seen in DESI data. Maybe the early universe formed black holes faster, contributing more dark energy, and that rate has been slowing. Black holes are also at the heart of some of the most radical ideas in modern physics. The information paradox asks what happens to information that falls into a black hole. The holographic principle was inspired by black hole thermodynamics. Wormholes, if they exist, are essentially black hole tunnels through space-time. Every deep mystery in physics seems to wind back to these strange objects. There's also the possibility that black holes themselves are gateways to other universes. In some theoretical models, the singularity inside a black hole isn't a true endpoint. It's a transition. The matter that falls in might emerge as a new universe expanding into its own dimension, parallel to but disconnected from ours. Our entire universe, in this picture, could have been birthed from a black hole inside a larger parent cosmos. Connecting this to cosmic expansion produces vertigo. If our universe is the inside of a black hole, then the cosmic expansion we observe might be the result of matter continuing to fall into the parent black hole from outside. The Big Bang was the moment a star collapsed in the parent universe. The accelerated expansion is the matter still pouring in. Dark energy is the residual pressure of the infalling stuff. Most physicists treat these ideas with caution. They're speculative. They're hard to test. They blur the boundary between physics and metaphysics. But they're also taken seriously by leading theorists. The math allows them. The data doesn't rule them out. If even one of these black hole-based scenarios turns out to be correct, our understanding of the cosmos would be transformed beyond recognition. The universe wouldn't be a self-contained system. It would be a node in a vast network of universes, connected through black holes, exchanging matter and information across cosmic generations. And in that network, even more bizarre possibilities open up. Possibilities that involve communication, signal leakage, and the strange thought that we might not be alone. If the universe is part of a multiverse, or a holographic boundary, or a simulation, or a black hole inside a larger cosmos, then a natural question follows. Could anything from beyond our universe ever reach us? Could signals leak across the boundary? Could we detect them if they did? This question used to be purely speculative. In the last decade, it has moved into serious scientific territory. Physicists have started designing experiments specifically to look for signatures from outside our cosmic horizon. Most have come up empty. Some have produced tantalizing hints. The cold spot in the cosmic microwave background is one of the most discussed candidates. It's a region of sky much larger and colder than any standard cosmological model predicts. One theoretical interpretation is that it's a bruise, a scar left by a collision between our bubble universe and another bubble during the inflationary epoch. The collision would have left a gravitational imprint that compressed the cosmic microwave background, creating exactly the kind of cold patch we see. This interpretation isn't proven. There are competing explanations. A particularly large supervoid in the line of sight could mimic the effect. Statistical fluctuations could produce rare cold patches naturally. Until we can observationally distinguish between these possibilities, the cold spot remains tantalizing but ambiguous. There are other candidate signals as well. Strange, large-scale alignments in the cosmic microwave background, patterns that hint at a preferred direction, periodic features in distant galaxy distributions that don't fit any standard model prediction. Each is suggestive, none is conclusive. But the fact that such candidates exist at all is itself meaningful. The universe shows hints of structure that doesn't quite fit the textbook story. The stranger possibility is that some cosmic signals might come from things we haven't even imagined yet. Physicists are increasingly aware that many proposed extensions of the Standard Model predict observable effects on cosmic scales. Hidden sector physics, dark photons, cosmic strings, vacuum decay events. Each could leave fingerprints in the data, fingerprints that have not yet been searched for systematically. The search has serious institutional support. NASA, the European Space Agency, and ground-based observatories are all building next-generation telescopes designed to scrutinize the cosmos with unprecedented precision. The Vera Rubin Observatory in Chile will image the entire southern sky every few nights, catching transient events and tracking subtle changes in galaxy positions. The Euclid Space Telescope is mapping the cosmic web in 3 dimensions to test dark energy theories. The Square Kilometre Array Radio Telescope is being built to capture faint signals from the most distant universe. Each of these instruments has the potential to discover something nobody has predicted: a new structure, a new particle, a new pattern, maybe even a new universe, leaking signals into ours. The hunt is sometimes called cosmic anomaly chasing. It's not glamorous. It's slow. It requires careful elimination of mundane explanations before any extraordinary one can be entertained. But the payoff, if anything is found, would be transformative. We would have direct evidence of physics beyond our current models, of a universe larger and stranger than we currently imagine. Even the hunt itself reveals something important. The fact that respectable scientists at major institutions are actively searching for signs of bubble collisions, multiverse scars, and exotic boundary effects shows how seriously these ideas are now taken. They're no longer fringe, they're frontiers. The Hubble tension might be one of the first signs that we're crossing one of those frontiers. A clue that the universe we measure isn't quite the universe we think we live in, that the rules we've written down are missing something that might come from beyond the edge. And whatever comes from beyond the edge could rewrite our understanding of time itself. Because the edges of cosmic time, the very beginning and the very end, are where physics gets weirdest. And we've already touched both. Suppose dark energy stays roughly constant. Suppose space keeps expanding at its current rate. Suppose nothing dramatic intervenes. What does the far future of the universe look like? The answer is heat death. And it might be the most desolate prediction in all of physics. In a heat death scenario, expansion continues for trillions upon trillions of years. Galaxies drift farther and farther apart. The light from distant galaxies stretches into infrared, then radio, then beyond detection. From any given galaxy, the rest of the visible universe slowly fades from view. Eventually, an observer in the Milky Way would see only the local group of galaxies that gravity has bound together. Everything else would have receded beyond the cosmic horizon. That's just the beginning. Stars continue to form for some hundreds of trillions of years. As they exhaust their hydrogen, they collapse into white dwarfs, neutron stars, or black holes. Eventually, all the hydrogen and helium in the universe is locked up in stellar remnants. Star formation ends. Galaxies become collections of corpses, dim and cold. Then the corpses themselves start to fade. White dwarfs cool over trillions of years, becoming black dwarfs. Neutron stars persist for unimaginably long times before potentially decaying through proton decay, if it occurs. Black holes evaporate through Hawking radiation, a process so slow that even modest black holes take more than 10 to the power of 67 years to fully disappear. Larger ones take much longer. After all, stellar remnants are gone. The universe is left with only photons, leptons, and possibly some residual particles drifting through unimaginably vast emptiness. There is no light, no matter clumps, no structures, just isolated particles in an ever-growing void. Time still passes, in a sense, but nothing happens forever. This scenario has a special place in physics because it represents the consequence of our currently best models. If dark energy is a constant cosmological term, and if the standard predictions hold, this is the future we're looking at, not a dramatic ending, a slow, cold, inevitable fading, the DESI data introduces a complication. If dark energy is weakening, the heat death scenario might be averted. A weakening dark energy could lead to expansion stalling, possibly reversing. The universe could recollapse instead of expanding into eternal emptiness. Some cosmologists, weirdly, find this comforting. A universe that ends in a big crunch is at least dramatic. It's the universe doing something. Heat death is the universe doing nothing forever. There's also a deeper question buried in the heat death scenario. As the universe ages and entropy keeps growing, the second law of thermodynamics seems to head toward absolute saturation. No more useful work can be done. No more thoughts can be thought. No more experiences can be had. Consciousness, in any form we recognize, might become impossible. This bothers physicists philosophically. Some have wondered whether unknown new physics could intervene, a late-time quantum fluctuation that produces a new universe, a vacuum decay event that resets everything, a bouncing mechanism that brings the cosmos back to a young state. Each is speculative. Each is a desperate attempt to avoid the apparent finality of heat death. What's striking is how the cosmic expansion mystery feeds into this question. The fate of everything depends on which expansion model is correct. A cosmological constant gives heat death. A weakening dark energy gives a big crunch or some other collapse. A phantom dark energy gives a big rip. The new DESI data sits ambiguously between these futures, hinting at multiple possibilities at once. Until the data sharpens, we don't know how the story ends, and maybe that's appropriate. The universe has refused to give us a simple beginning or middle. It might also refuse to give us a simple ending. But there's one more piece to consider, because as the universe ends, whatever form that ending takes, the question of what we know and what we can know becomes itself uncertain. Some scientists believe that future observers might lose access to information we currently take for granted. The truth is being erased, slowly, by cosmic expansion itself. Imagine an alien astronomer in some distant epoch, billions or trillions of years from now. Suppose this astronomer has the same scientific capability we have today, the same telescopes, the same theories, the same methods. They look out at the cosmos and try to figure out what kind of universe they live in. Here's the chilling thing. They wouldn't see what we see. They couldn't reach the same conclusions we have. They might never even discover that the universe was once full of galaxies, full of cosmic microwave background radiation, full of evidence of a Big Bang. Why? Because cosmic expansion is slowly erasing the data. As the universe ages, distant galaxies recede beyond the cosmic horizon. Their light fades, redshifts, and eventually disappears. The cosmic microwave background, the most important fingerprint of the Big Bang, gets stretched into ever longer wavelengths. By the time the universe is hundreds of billions of years older, the cosmic microwave background will be undetectable with any conceivable instrument. By the time it's even older, only a few isolated galaxies will be visible to any observer. Astrophysicist Lawrence Krauss made this point in a now famous paper. Future cosmologists will be unable to determine that they live in an expanding universe. They will not see distant galaxies. They will not see the cosmic microwave background. They will see only their own local galactic group, gravitationally bound, looking like an isolated island in a featureless void. They might conclude that they live in a static universe, infinite and eternal. They'd be completely wrong, but they wouldn't know it. The data needed to figure out the truth would have been erased by the expansion itself. This is one of the most haunting realizations in modern cosmology. The universe isn't just a place. It's a place whose evidence is gradually disappearing. We happen to live in a privileged epoch when the cosmic microwave background is still detectable, when distant galaxies are still observable, when the imprint of the Big Bang is still legible. Future observers won't have those privileges. What's especially relevant to our central mystery is that this erasure is already underway. The most distant galaxies we see today are receding so fast that their light is barely reaching us. Each year, more of them slip past the cosmic horizon, The universe of available data is shrinking, slowly, almost imperceptibly, but measurably. This raises a disturbing question. What if some of the answers to current cosmic mysteries are already gone? What if the structures or signals that would have explained the Hubble tension or the weakening dark energy were once visible but have since faded beyond our reach? Maybe early observers, billions of years ago, could have seen things that we cannot. There's also the reverse worry. Are we missing things that future observers won't be able to see either, but that we still might catch in time? The Vera Rubin Observatory, the Euclid Space Telescope, the James Webb Space Telescope are all racing to capture the universe before more of its evidence vanishes. There's a sense, in modern cosmology, of urgency. The story is being told now, and someday it won't be tellable. Some philosophers have used this insight to argue that we shouldn't fully trust any cosmological theory. If our window into the universe is constrained by what hasn't yet faded away, then our theories might be biased by what's currently visible. The truth might lie in things we cannot observe, things that have already crossed the horizon, things we'll never see. In a sense, this turns the cosmic expansion mystery into a kind of detective story with shrinking evidence. We have to solve the case before more clues disappear. The Hubble tension and the weakening dark energy might be the last loud signals from an underlying physics that's increasingly being hidden by the very expansion they describe. Whatever the truth turns out to be, the cosmos is teaching us humility. It's an enormous, ancient, evolving system. Our access to it is partial, our perspective is fleeting, and some of its deepest secrets might already be beyond our reach. But not all of them. The ones we can still grasp are pointing us towards something extraordinary, a revolution in physics that's just beginning to take shape. And the next chapter of that revolution might come from a place nobody expects. For most of cosmology's history, astronomers have worked with limited tools, optical telescopes that capture visible light, a handful of radio dishes scattered across the world, a few space-based observatories. The data, by modern standards, was thin. Today, that's changing fast. The James Webb Space Telescope is just the beginning. Already, it's overturned assumptions about how galaxies and black holes form. Its successor for infrared observations is being designed. Together with the Vera Rubin Observatory, the Euclid Space Mission, and the Square Kilometre Array, the next decade will produce more cosmic data than the previous century combined. The Vera Rubin Observatory, perched in the Chilean Andes, will scan the entire southern sky every few nights. Over 10 years, it will produce a movie of the visible universe. Every galaxy, every supernova, every transient event will be catalogued. Astronomers will track how cosmic structures evolve in real time. The Hubble tension, the dark energy puzzle, and many other mysteries will be tested against staggering volumes of data. The Euclid Space Telescope is specifically designed to measure dark energy. It's mapping the three-dimensional distribution of galaxies across nearly a third of the sky. By measuring how the cosmic web has grown over billions of years, Euclid will tell us whether dark energy is truly a constant, whether it's evolving, and whether the standard model needs revision. Initial results have already begun appearing, and they corroborate hints that dark energy is not behaving as the simplest cosmological constant model predicts. The Square Kilometre Array, an international radio telescope network being built across South Africa and Australia, will detect the faintest radio signals from the universe's most distant epochs. It can study the era before the first stars formed, called the Dark Ages, where ordinary telescopes cannot penetrate. By mapping hydrogen distributions billions of years ago, the SKA will reconstruct the universe's full expansion history, settling many open questions. The Atacama Cosmology Telescope and its successors are continuing to refine measurements of the cosmic microwave background. They're not just measuring temperatures anymore. They're measuring polarization patterns, gravitational lensing of the early light, and tiny secondary signals that encode information about cosmic structure. Each new measurement either tightens the Hubble tension or hints at how to resolve it. The CMBS-4 collaboration, planned for the late 2020s, will be the most ambitious attempt yet to read the universe's earliest signal. It might detect primordial gravitational waves. It might confirm or rule out specific inflation models. It might find new anomalies that point to physics beyond the standard model. The combined effect of all these telescopes is going to be transformative. By the early 2030s, cosmologists will have access to data so detailed that current uncertainties will shrink to near zero. The Hubble tension will either be resolved or definitively confirmed as a genuine crisis. Dark energy will either be revealed as a true cosmological constant or shown to be evolving. The smoothness of space, the existence of large-scale anomalies, the nature of dark matter, all will be tested with precision that today's instruments can only dream of. The stakes are enormous. If the standard model survives, the cosmic mysteries will be resolved as subtle effects within the existing framework. If it doesn't, we'll be looking at the most significant physics revolution since Einstein, maybe bigger. What's remarkable is how this revolution is playing out in real time. Every few months, a new paper appears. Every year, a new measurement narrows the possibilities. Cosmologists today are living through an era when fundamental questions are being actively answered. Future generations may envy us or pity us, depending on how messy the answers turn out to be. Whatever happens, we're approaching a turning point. The universe has been hinting at something deeper for years. Soon, we'll know whether those hints add up to a complete revolution or whether they fade back into the noise. And that brings us, finally, to the largest question of all, the one that has lurked behind every chapter of this exploration. What does it all mean? What is the universe actually telling us? Step back. Look at everything we've covered. The Hubble tension, the KBC void, the weakening dark energy, the phantom and the quintessence, the smoothness problem, the missing dark matter, the early massive galaxies, the timescape theory, the cosmic microwave background anomalies, the Mond alternative, the entropic gravity hypothesis, the multiverse possibility, the bouncing universe, the simulation question, the vacuum catastrophe, the cosmic web mysteries, the fine structure variations, the black hole connection, the heat death, the data being erased, the new telescopes coming online. That's a lot. It might feel overwhelming, but there's a single thread running through all of it, a common message that the universe seems to be sending us right now. The message is this: our current model of the cosmos is incomplete. Notice, this isn't the same as saying it's wrong. The standard cosmological model has been extraordinarily successful. It predicted the cosmic microwave background. It explained the abundance of light elements. It accounts for the broad structure of the cosmic web. It correctly describes how galaxies form, how stars evolve, and how the universe expands on a basic level. Most of its predictions have been confirmed by careful measurement. The model works, but it doesn't work perfectly. And the places where it fails are clustering together in suggestive ways. The Hubble tension, the S8 tension, the early galaxies, the dark energy evolution, the large-scale anomalies. These aren't random failures. They're connected. They might all be hints of the same underlying physics that we haven't yet discovered. What kind of physics? Nobody yet knows. It might be a modified theory of gravity. It might be a dynamic dark energy field. It might be a connection between quantum information and space-time. It might be a new symmetry, a new particle, a new dimension. It might be all of these. It might be none. The pattern reminds us of moments in scientific history when revolution was imminent. Before relativity, classical physics had small but persistent failures. The orbit of Mercury was slightly off. The speed of light didn't fit Newtonian mechanics. The luminiferous ether was missing. Each individual problem could be patched. Together, they pointed to a deeper revolution. Einstein's theory swept them all away. Before quantum mechanics, classical physics had different small failures. Atomic spectra didn't fit. The photoelectric effect was strange. Blackbody radiation defied prediction. Each could be patched individually. Together, they demanded a complete rethinking. The quantum revolution emerged. We may now be in a similar moment. The cosmic puzzles might individually be solvable with minor adjustments, or they might collectively require a new framework that subsumes our current understanding, the way Einstein subsumed Newton, the way quantum mechanics subsumed classical thought. What does this mean for you, for all of us? It means we're living through a rare period in history, a moment when fundamental questions about the universe are open and the answers are within reach. Within decades, possibly within our lifetimes, the cosmic expansion mystery will likely be resolved. We'll know whether dark energy is constant, evolving, or an illusion. We'll know whether the universe is a simulation, a hologram, a bubble, or something new. We'll know whether physics needs a small fix or a complete rewrite. The answer will reshape our understanding of reality itself. It will change how we view our place in the cosmos. It will affect the way future generations think about the largest questions: the age of the universe, the size of the universe, the fate of everything. It also means the universe is still surprising us. After all our science, all our equations, all our brilliant theories, the cosmos still has secrets, big ones, deep ones, the kind that humble even our greatest minds. Science isn't a finished project. It's a living process, and we're privileged to watch it unfold in real time. Every photon arriving at our telescopes carries a story. Every measurement deepens or shifts the picture. Every anomaly is a clue. The cosmos is whispering to us, and we're slowly, patiently learning to listen. The next decade will tell us whether what we hear is a confirmation or a revolution. Either way, it will be one of the most extraordinary chapters in the history of human curiosity, and we get to live through it. Thank you for joining the journey.